So, your brain can't function when you're learning functions. But y equals to mx plus c is actually really easy.
What if the function?
Essentially, functions assign one output for every input value. There are three types of relations, which is not really complicated compared to this. Firstly, you have the one-to-one relation, which means that for every input value, there is one unique output, which means it is a function because every input has one output. These are just two simple examples of one-to-one relations. You also have the many-to-one relation, which means that different input can share the same output. It is still a function as one input has one output. And here are two examples. Wait, what's this bracket? So, it is just a modular sign which turns every negative value into positive. So as you can see, the 2 remains as positive, whereas the negative 2 turns to positive 2. Lastly, we have the one-to-many relation, which means one input leads to many output. So as such, it is not a function. And here are just two simple examples. Rule of thumb, how do we determine if any graph is a function? All we need to do is just draw vertical lines on the graph. And if the lines only intersect the graph once, it is a function. However, if any of the lines intersect with the graph more than once, it is not a function. Mathematicians are just too bored, and there are a lot of functions that we need to learn. Firstly, we have linear, which is in the general form of y equals to mx plus c, and it is the only straight line. The m here stands for the steepness or the gradient of the graph, and the larger value of m means that the steeper your graph is. And c refers to the y-intercept, which is the point where your graph is going to intersect your y-axis. Next, you have quadratic graphs, which means that the highest power of x is raised to is 2. And the reason I call them quadratic graph is because they are either in a happy phase or a sad phase. When your a, or when your coefficient of x squared is positive, it will always be a happy phase. However, if it is negative, then it will be a sad phase. Next, we will have the cubic graph, which means that the higher power your x is raised to is 3. And no, it doesn't look like a cube. Instead, it looks something like squiggly lines. We also have the trigonometric graphs, which is sine x, cos x, and tangent x, which all continues indefinitely. Lastly, we have the modulus graph. Remember, it just turns all the negative value into positive values. So, as you can see, the first and second graphs are just reflection along the x-axis. So it means that whenever you multiply negative by a graph, it just reflects the graph along the x-axis. Function notation. Since now you're in high school, we need to level out the playing ground. And instead of using y, we use this, where f refers to the name of the function, x is your input, and whatever is behind the equal sign is your output. So in this case, g is the name of your function. And in this case, g is the name of the function, and t is your input. Why do we need it? Because instead of having y equals to 4, it actually gives us more information. For example, f tells us which function we are referring to, and the number inside the bracket tells us what is the input. Wait, what's this?
It's the same shit.
Where f is still the name of the function, x is still your input, and whatever is behind the arrow sign is your output. But normally, we use the previous notation, unless you're extra special. Why Why do we need to learn functions? Functions describe how this cat relate to. Functions describe how numbers relate to numbers, which help us find patterns and understand the world. It is useful in this stuff and even shows the probability of your school getting hit by a meteorite. If your school does really get hit by a meteorite, the first thing you should do is deliver me the meteorite. Functions must only have one output for every input, and this is why. Consider this function. Your input is the number of days you spend scrolling TikTok. Output is the number your mom called you a failure. So, with this function, by plugging in the number of days you spend, we can know the number of times your mom called you a failure. So, it is useful. However, let's say if you have not a function, which is a one-to-many relation, when you plug in the number of days you spend, you actually get two outputs. So, which is kind of useless because you don't know which output to refer to. So, it's a failure. Composite functions. No, it is not referring to a composer sitting down. Anyways, it refers to taking the output of one function and plugging it into another function. Like this. Oh wait, I mean like this. Yeah. So it can be the same function, meaning you plug in the function of f, then you plug it into the same function again, like this. Oh, yeah, like this. So this is just a simple example. Or you can plug it into a different example. In this case, we plug it into the function of g, then take the output and plug the output into the function of f. Now we have two really simple examples. Firstly is function of g of fx, which means that your input is put into the function of f, then into g, which gives you x plus 1 squared. And the second one is function of f gx, which means that your input is put into the function of g, then only the function of f. As a result, you got x squared plus 1. As you know, the order actually matters. The function of g fx is different from f gx.
But actually,
the order doesn't matter when f and g are literally the same thing, because it just means that you're doing the same operation again.
Is common sense.
In addition, the order doesn't matter when f and g are inverse of each other, which brings us to the question, what are inverse functions? Let's say you want to build one sword, and you need 2 emeralds to build one sword, so you spend 2 emeralds. 10 years later, you looked at your colossal gargantuan massive sword, thinking how much you spent on this sword. So, since you divide by 2 to get the sword, now you need to multiply by 2 to get the amount of emeralds. And we will call this the input of function, and this the output of function, the input of inverse and the output of inverse. As such, we will get this relationship. But in nerd terms, the inverse function actually means that taking the output and giving back your original input. For example, you have these two functions, and you forgot what was your original input to get the output 3. So you plug in 3 into your inverse and you got 2, which means that your initial input is 2. Note that these two are completely the same and will always give you back your original input. Only one-to-one functions have inverse functions. Why? Many-to-one functions do not have inverse functions because its inverse would be one-to-many, which is not a function. Rule of thumb. We use the horizontal line test to determine if your function has an inverse. It's the same as the vertical line test, instead you just draw horizontal lines. As long as the horizontal lines touch your graph at only one place, it is a function. However, if any of the lines touch your graph at more than one point, it does not have an inverse. How do we find inverse? You simply swap x and y, make y the subject, and replace y with the inverse notation. Relationship between function and its inverse. Each function is the reflection of the other in the line y equals to x, which is this line. So we have a function and its inverse right here, and as you can see, it is a reflection. Domain and range. Domain refers to all the possible input values, which is the x values. Consider this function x plus 1. And since your x can be virtually anything, we write it like this, which means x can be any real values. Special case. So you remember that we can't have 0 in the denominator. So as division by 0
Is a unique and problematic special case.
described by Wikipedia. As such, with this in mind, with this function, x can be anything but not 0. And for this function, x can be anything but not negative 2. The next special case is that when you have x inside the square root, the stuff inside the square root can't be negative. Nerds, I know you're probably looking the video like this, but imaginary numbers are just too deep for this video. So we'll just assume that stuff inside the square root can't be negative. So for this function, the domain will be more than equals to 0. And for this function, the domain can be more than equals to negative 2. Range. Range is all the possible output values, which is the y values. And for this function, since y can be anything, we write it like this, which means y can be any real values. The first example is a quadratic graph. The first, we have a smiley face quadratic graph, as the coefficient of x squared is positive 1. The range for this graph is that y will always be more than the minimum point, which is 1. So y will be always more than 1. Next, when the coefficient is negative, you have a sad graph. So we need to identify the maximum point, and the range will be always less than equals to 1. Exponential graph. Let's say you have y equals to 2 to the power of x, which looks like this. Since you will never get 0, the range will be always more than 0. And we have 2 to the power of x plus 1, which actually just shifts the graph up by 1 unit. As such, the range will be y more than 1. So now you know the domain and range. And it's time to introduce you to restricting domains. Remember the bubble who gave you this card? Now you can do the same to functions. Restricting domain means that we are considering some part of the functions only. For example, x plus 1, the graph continues indefinitely. But if you restrict the domain to between 3 and 9, you sort of cut out the part you want only. As such, restricting domain is just like cutting the functions. Note that the inequality symbol actually matters because when you have the equal sign, it means that that point, 0, is considered. However, if you just put this sign, it means that 0 is not considered as a part in the graph. So you'll have something like a hole. Why would we want to do that? It's because mathematicians, this time is actually useful. Remember we said that many-to-one functions don't have inverse, but through restricting domain, we can make sure inverse functions are possible for many-to-one functions. For example, if I restrict the domain for this function to x more than 0, we're only taking this part, which is a one-to-one function, which allows it to have an inverse, which is also a one-to-one function. However, you need to be careful when restricting the domain, because if you restrict the domain incorrectly, it will remain as a many-to-one function, and it will not have an inverse function. Next, restricting domain also allows us to make sure that composite functions exist. In this case, the function g of x says that only numbers that are more than or equal to 0 are worthy of becoming its input. So we need to make sure that the output of f meets this requirement. Let's consider some numbers. Firstly, if the original input is 1, plus 1 you get 2, And since 2 is more than 0, it can be an input for g, which gives us our final output. However, when our initial input is something like negative 3, plus 1 we get negative 2, which is lesser than 0, so it can't be an input for the function of g. And here is where an error occurs. As such, since we know that x plus 1 must be more than 0, and through solving this inequality, we know that x must be more than equals to negative 1. As such, we introduce this restricted domain to fx to make sure that composite functions exist. Now that we know what's domain and range, it's time to introduce you the second relationship between a function and its inverse. Remember this relationship? Yeah. Now just replace input with domain and output with range, which gives us this following. An example would be square root of x plus 2, of which its inverse will be x squared minus 2. Since we know the domain for g of x is x more than negative 2, we know the range of the inverse must be more than negative 2. And since we know the range of g, which is more than 0, we know the domain for its inverse. Summary. Function gives one output per input. Only one-to-one and many-to-one are functions. Function notation looks like this. Composite function take output of function and plug it into another function. And f g x is not the same as g of x unless f and g are the same or are the inverse of each other. Inverse functions take output and gives back the original input. Only one-to-one functions have inverse. Domain refers to all the possible input values. Range refers to all the possible output values. Restricting domain allows us to ensure that inverse functions are possible for many-to-one functions by changing it into one-to-one function. It also allows us to ensure that composite functions are valid. Lastly, the vertical line test allows us to know if it's a function or not, and the horizontal line test allows us to know if the function has an inverse. These are just some additional resources for nerds. Thank you for watching.